Hello, everyone. Can you hear me? Well, yeah? Okay. So, my name is Pedro, and this is my colleague, Carlos.
Hi,
And
guys.
today, we'll make a presentation on static and dynamic analysis of events for threat detection. We both work at the Siemens Cyber Defense Center, which its main mission is to monitor the infrastructure of the Siemens worldwide. What this means is that we collect all of the security-related events from Siemens in order to analyze them and detect potential security threats. The Siemens Cyber Defense Center is a joint venture between Portugal, Germany, and the United States. And just here in Portugal, we are more than 50 members. In this presentation, we will we'll focus more on the detection aspect of cybersecurity. Just to give you some context for you, you might not be so familiar, but there are typically three major fronts to cybersecurity. You have your prevention, which are the mechanisms that you put in place in order to assure that certain attacks will not occur. For instance, the deployment of a firewall to block certain packets. You have your detection mechanisms, which are the systems that you can put in place in order to analyze events and detect potential malicious threats. And then lastly, you have the mitigation, which is typically the last line of defense. And the mitigation measures you use to lessen the effects of an attack that has already occurred against one of your systems. And as I said, we'll be focusing more on the detection aspect, more specifically on a next-generation detection platform that we have built for static and dynamic analysis of events. So, what problems do we face which led us to build such a platform? First of all, the global malware rate is increasing at an alarming rate. In 2018, we had 137 new malware samples identified, which gives us about 200,000 new malware samples identified each day. So attackers are really busy trying to come up with new ways of penetrating your defenses. Additionally, not only we are seeing more attacks, but also they are becoming more sophisticated. We are seeing attacks with the ability to spread and remain undetected by either deleting themselves or by changing each time they propagate. And lastly, to further aggravate this issue, the attack surfaces of companies nowadays are very large. For instance, typically, large companies will have an on-premises infrastructure. They will have cloud infrastructure, as well as support for instance, mobile applications. So attackers know this, and they will try to penetrate your defenses using many attack vectors. So given these problems, the question becomes, how can we efficiently solve them? What are the questions that we need to answer in order to solve these particular problems? One of the questions that we can ask is, how can we efficiently scale? Because we have a large number of attacks, we need to analyze more data, so we need to be able to scale. Additionally, the second question can be, if the complexity of attacks is very high, and if they are constantly changing, how can we prepare for this constantly changing landscape, and how can we prepare for new threats? So now that we know the problem that we want to solve, we want to know why we want to solve this problem. Why do we care about security? And one of the first aspects is that your information is valuable. You wouldn't just give your golden nuggets to anyone, so you need to protect it. Additionally, attackers will not only be after stealing your information, they'll also be after disrupting your access to that information in order to make a profit. One example of this is the WannaCry malware, which effects still last to this day, that started in 2017. And an estimated of 230 malware computers were affected by this malware, which means that a lot of people and a lot of companies had their data encrypted and were unable to access it, thus they lost a lot of money. Additionally, your reputation also matters. If users don't trust your company with their data, they won't use your applications and products. Lastly, attackers can also be after after disrupting your services, and how good are your services if your applications if they are unavailable. So now that we know the problem that we want to solve and the motivation behind solving these types of problems, we'll try to address the first question, which is how can we efficiently scale? And in order for you to understand how can we efficiently scale, I have to show you our former infrastructure and why did it fail in this aspect. A typical detection environment, and this is a very simplified illustration, will have a set of events coming in from our infrastructure, which is the data that you want to analyze. And these events are typically fed to a CM system. For those of you who don't know, CM stands for Security Information and Event Management. And these systems will correlate the events in order to find malicious patterns. And once they find a malicious pattern, they will output an alert which can trigger then a notification, and that notification can then be analyzed by one security analyst. And these CM systems, at their core, they will have a correlation engine. And this correlation engine has a set of rules which contain the conditions where an event or a set of events should be considered malicious. To give you a little bit more detail on this, you can have a set of events which are simply arrays of key-value pairs, and you can have very simple rules which will look at the fields for those events, and if that field matches a certain condition, then an alert is triggered. For instance, you can have a very simple rule like this one, where we are looking at the action field, and if the action field equals to a part scan, you will then trigger an alert. Of course, this by itself, it's not very useful. That's why we have more complex rules. We can have windowed rules where you can specify a time interval and a grouping condition to group events in real time together. For instance, you can group all of the events for a single user and try to understand if that user attempted to log in into several servers but failed. So you can have a specific threshold for failed login attempts and then trigger an alert. And the cream of the crop, the really important thing about these correlation engines are the correlation rules, which will cross this information. So if you have 2 alerts for the same user, you can generate a third alert more critical because that user is for sure attempting more than one malicious action, and something must be done in order to stop it. This is what our former solution looked like. We had 3 CM instances, and these CM instances were based on commercial solutions, which, first of all, they are very costly due to their licenses, and also they didn't scale horizontally. So we had to split the events across these 3 instances, meaning that we wouldn't have cross-correlation, so we'll lose one of the main features because the data that is coming into one of the instances will not be correlated with the other one. The second problem is that each one of these instances will need its own copy of the data and copy of the rules. And because this is a very closed solution, we weren't able to build any integration with their APIs. Every time that we needed to do a change in one of the systems, we also had to log in into the other systems to do the same change as well, which is very cumbersome. So there is an overall lack of flexibility with this solution that we want to address. But we have a big operational challenge. First of all, Siemens, we monitor in the Cyber Defense Center more than 350 endpoints, which translates to about 60,000 events per second, which roughly gives us 6.2 terabytes per day, which is a lot of data that we need to handle. So we not only need to handle a lot of data and scale, but also handle the flexibility issues. So we tried to come up with a new solution that was able to address with these problems. And the first thing that we did was to change our correlation core. We've built a new correlation engine from scratch using Apache Flink. For those of you who don't know, Flink is a distributed stream processing engine. And you can program with their API your own direct cyclic graph. What this means is that you can develop a pipeline where your events will come in from a source node and get transformed along your pipeline until you get your final result at the end of this graph. And the next change that we did was to add Redis as our data store, because our security rules need detection lists for optimization. For instance, you can have a whitelist in Redis, a set of keys which represent whitelists, and every time that a certain field of an event will match that whitelist, it gets discarded. So it wouldn't get to the end of the pipeline. The next big change was also to add Kafka as our message broker, because before we stored all of our data in a database and we had more of a batch approach. And this wouldn't give us the quick response that we need. So in order to move towards a more stream-based approach, we added Kafka as our message broker. And all of our applications can then read data from Kafka, and the data can keep flowing, and you can keep generating alerts and using them as a feedback to Kafka again to be reinjected again into our correlation engine. And what acts as a control stream, and what's the secret about this correlation engine, are its rules. And these rules are written using an API that we developed. And every time there is a change in one of the rules, someone pushes a new rule file to Git. I will talk in a moment a little bit more detail about the language, but those rules get compiled and then distributed to the pipeline. To talk a little bit more about Apache Flink, as I said, is a distributed stream processing engine. This means that all of the nodes that make up your pipeline can be distributed across several machines. And this allows the application to scale very well. Additionally, it has several libraries, for instance, for complex event processing, machine learning, and other use cases. And it also offers you an API both in Java and in Scala. And why did we chose Flink and not something else? First of all, because of its performance. It has very low latencies without throughputs. And it offers something that, at the time, no other tool offered, which was exactly once consistency in stream. And this allows us to process an event exactly once and only once. And it does this by recovering its state exactly as it was when it failed. It also allows for high availability. It's very scalable and very flexible. An example of an application that you could build in Flink looks kind of like this. So you will have, this is the pipeline we are trying to build. So we can read simple strings from a socket, and then we can transform those strings by simply parsing them into an event object. And then you can filter data by inspecting that event object. For instance, we are discarding everything that is not a port scan, and then at the end of a pipeline, which is the sink, we simply print the data to the console. And that's it. This is a very basic example. Of course, our pipeline is a lot more complex than this. I'm showing here just a subset of our pipeline, but we have our events coming in from Kafka into our graph, and then we have the rules. As I said, every time a user pushes a new rule into Git, this rule will get fetched by the correlation engine. And the correlation engine will compile that rule, and then it will send it to all of the nodes. And all of the nodes will have a particular role. For instance, the filter node will apply the filtering conditions from a rule. And the filtering conditions will say if an event should be, or a set of events should be considered an alert. And then this part of the rule will be stored here in an array, and every time an event flows into this node, it will get processed by all of those rules that are stored in this node. An example of a rule, by the way, this language was developed using Antler, and we then developed a Visual Studio plugin for highlighting and auto-completion. And just a quick example of one of these rules here. But you can have, for instance, this segregation rule, which has a clause that specifies the sources. And the sources are the events that should be processed by the rule. In this case, we have Kerberos events. And then you can have a filter which says that when an event should trigger this rule. In this case, the event will trigger this rule if it is a failed authentication. And then we have our grouping conditions. This rule will allow you to group all of the events by user, so we'll have different windows for each user, and then you can count this case, it's a sliding window, a 2-minute window that slides every minute, and you can count the distinct hosts that user tried to log in but failed. And then if that total is greater than 3, we here will trigger an alert. And one interesting part about these rules is that you can enrich them by querying Redis. For instance, we have here a query in Redis which uses the source user to get its name and the region. And then we enrich the event by appending a new message saying that this user from this region attempted to log in but failed several times. And then this rule is broken down into several parts before it's used in the previous pipeline. So the sources will be sent to the sources node, the filter part of the rule will be sent to the filter node, and then they will have their respective rules to continuously apply the computations to the events as they come in, and we don't need to stop and start a job every time a user deploys a new rule. And this is how we can do the static analysis of events.
Thank you, Pedro. So everybody can hear me, right? Okay, so we will change a little bit the direction of this talk, and now we will discuss the problem Pedro just spoke. So attacks are becoming more and more sophisticated, okay? What does that mean? Fair point, guys. Therefore, we will discuss a very concrete example, which is DGA. For the ones that don't know what that means, basically from Wikipedia, it is domain generation algorithm, and itself, that's not malware. It's only a technique used by malware makers to bypass static defenses. So they generate multiple domain names. Okay, why they do that? Let's try to figure that out with a very simple example. So this is the normal behavior of a network. You have someone in your company accessing Facebook, that's okay, we don't care. However, if you have some infected hosts, it will try to access a website, for example, IamEvil.com, and you will look, okay, this is suspicious, I need to tackle this issue. Okay, why is malware trying to access this server in the internet? Is because, for example, it's going to try to exfiltrate your data to steal the information, or maybe it's a very lightweight malware and is going to try to pull some plugins to power up and do more damage. So on the other side of the trenches, we will try to stop it. A thing you can do is blacklist. You can just say, okay, I don't allow communications for this domain. That works, but it would work better 10 years ago, not now. Why is that? Because now these malware makers, they will use the so-called DGAs to evade your defense mechanism. The DGA will produce multiple examples with some randomness due to a seed they use, and if you try to block one, they will produce another one, so it's kind of not a scalable approach. It's really hard to maintain. This approach, traditional approach, won't scale against these new types of malware, okay? Here, a quick code example of Benjori DGA. As you can see there, you have the seed, which is the domain, and then here you have a function that will be used for the mutation. It will change only the first 4 characters of the seed in a random way, more or less. It's not really random, it's pseudo-random. And this is very simple. There are other use cases where it's really hard to find a pattern. Usually, as a defender, you don't have access to this information. You need to do reverse engineering, which is a time-consuming process. So we need to get a way in order to, as the threat shows up, you can defend against it or detect. So since PixelScamp is more about challenge and not so about talks, I would like your help, guys, to try to identify between all of these domains which ones are malware and which ones are legit. Can you guys help me? I will give you like 3-5 seconds to think about it. And by the way, there is a prize for the ones getting it right. So someone want to give the first attempt? Okay, let's split this. If we look into that, we need to go for quick wins. So we have a couple of .nl examples, so which means Netherlands, and Netherlands usually is a nice country, people is peaceful, so we can just drop. These are legit domains. Then let's go for the quick wins for malware. And for that, I would go for long strings. So I will pick this for sure, and this for sure. Do you guys agree with me? Who is against? You are against? Who is against me? Can raise the hand. Just 2 guys, okay. Surprise, surprise. It's really hard to detect malware. Because although our eyes are really wonderful things, they have fundamental limitations. And that's the big problem. And what is really funny is that the long string is actually the name of a town in Wales. Looks like that someone that is the Pixel Scam hackathon after 48 hours just fall asleep in the keyboard, you know, and produce that. For the ones that were participating, here are some coins. I'm sorry. These coins you can use in Siemens booth. So guys, please enjoy. You can get a unicorn or a Web Summit ticket, okay? Okay, now let's get serious again. What tools do you have available to tackle this issue? So first tool we can come up to our minds, maybe rules, heuristics, also regular expressions, which by the way is a lovely tool. I really like to use regular expressions to extract the information from text. But those 3 tools have the same pitfall. So they depend on our human cognitive capabilities. And as we did look into the challenge, we are not able to really produce a pattern that can detect DGAs. There are a multitude of different families of DGAs, a multitude of seeds, and if you combine both, it's just a huge number of combinations. As a human, this is a task that we cannot solve. However, there is one more option, which is machine learning. I'm not going to say AI. This is not a commercial talk. Sorry, guys. Here is my lame joke. Ta-da! OK, now I'm going to try to walk you through the process of detecting DGAs with machine learning. Who is not familiar with the machine learning workflow? Can you raise the hand? OK, a couple. So I will just ignore you guys. I'm sorry. You can leave. Joking, joking. So I have here a very simplified machine learning workflow, and I will walk you through the steps with an example so you can better understand the approach. So what is raw data? Raw data is our HTTP request that you collect from the proxy logs. It contains multiple components. For this use case, we want to clean it, and by that I mean I want to extract the domain names. Valid domain names, which are strings that I can parse the domain. Because you can imagine, in a big network like Siemens, there is always parsing problems and weird strings and stuff going in that part. So let's get rid of the trash. Then, one of the most important parts in a machine learning workflow is the feature extraction. So here, you try to transform the information from that string into some statistical properties, which you call attributes or features. Simple example is the length of the domain. Here is simple, 15. A bit more complex feature that you can come up with would be non-letter ratio, where you just count the number of letters, divide by the string size, and is 1 minus that. And another example, just for your awareness, ratio of consonants to vowel changes. Basically, from D to O is 1, M to A 2, and C, sorry, done. Okay, got it back, sorry, guys. I don't have more coins. And then C to O, it's 3, and you just do the math, and you get one more feature. Last part is the modeling part, where you just use any traditional machine learning algorithm in order to build your model. In this example, I can talk you about random forest. I will make it very simple. You can think it as a group of decision trees. And what a decision tree does is it creates if-else rules, but not my if-else rules, rules based on the data, historical data. So one example, if in my historical data I have domain names which are longer than 200 characters, and all of them are malware, it will produce that rule, okay? And then it will basically branch and try to find another rule which can split this information, and so on, so on. This provides good results, apparently very good results, 85% accuracy, but the problem is that false positive ratio, 30%. In security, this means you cannot go to production. This means you are done, your security analyst will kill you. Because every time you produce a false positive, someone on the other side will need to look into that. And in the end, if they find out it's a false positive, they just think, okay, I just wasted my time. I need to kill that guy. So we need really to reduce this problem and avoid it. Therefore, we try to move one step further. And the next option is deep learning, which is a subset of machine learning. And this guy, Andrew Ng, for the ones which don't know him, is basically the creator of Coursera. He was behind Google Translator, also behind some AI services in Baidu. And he just says that traditional machine learning algorithms won't scale with data. This new generation, which is deep learning, can do that, which is powerful because at Siemens we have this huge amount of logs, as Pedro told you, 6 terabytes of data per day, and we can afford to use those algorithms then. Apologies for the complex slide. So this is the building blocks for you to solve the issue with deep neural networks. The first thing you need to do with your data is encode the string. You no longer need to do feature extraction. It will save you that effort. It's going to automate that process. You just need to encode and then starting adding those deep neural network layers. The first one I recommend to use always is the embedding layer, which will produce a more dense representation of your initial information. And during the learning process, it will update the vector numbers in order to try to come up with some information. It will start creating that information. Then you can stack more layers, you can combine, you can just stack them one on top of the other. You can go for a way you put stacks in parallel. And the 3 high-level families of layers for these deep learning networks are the recurrent networks, the convolutional networks, and the dense layers. So you can solve the problem with either one of those or combine them. I will recommend you to try out to get a feeling. And in the end, you just need to reduce all this information into an output. Our problem is binary. We are looking for a 1 or O answer. Basically, malware, not malware. Or in this case, DGA, not DGA. Now some code. So if someone wants to also take a picture to reproduce that later in home, feel free to do that. This is one example. And as I was saying, you can come up with very different architectures, and all of them will produce very good results. Really very good results. If someone is taking pictures, I can go back. Sorry. OK. So to wrap up, the deep learning approach will yield always a very good set of results. It's impressive. And the benefits is that you save your time in doing manual feature extraction, and since you don't have to do that, you no longer expose the risk of having those features, because on the other side, your opponents are smarter, and they are always one step ahead of you, okay? You cannot go above that. You can just be very close to them. And if they know that you are using machine learning, they will come up with a solution to evade your traditional features. With the deep learning, you are creating a very complex network, which is really depth and wide, and it's very hard to bypass this. Overall benefits of solving the problem with machine learning is that you don't need external information. Example, you don't need the registration details of that domain, you don't need domain reputation information, and in the end, if you need to deploy this in a real-time solution, since you no longer have these dependencies, you can go really, really fast. Okay, final question that we have for today is, with this huge landscape of threads and a very big attack vector, how can we defend? That's really the big picture. This question is translating the big picture. And there is no silver bullet here. What we are trying to do is combining all the defense mechanisms possible, the static ones, the dynamic ones, and by combining them, we hope to augment our detection effectiveness. So don't put all your eggs in one basket. Altogether, this is the architecture. This is hybrid architecture. Some components are on premises, others are in AWS. We try to go for serverless services. The ones with this detection thing means that they are producing alerts and tickets. We have also storage for some rapid access. So we have this hot zone on Elastic to hold more data, more historical data, and we are talking about 1, 2, or 3 petabytes per year. We have a data lake in Amazon based on S3 and Athena. Also very important, keep everything simple and modular. Bear in mind that nowadays architectures should be without an end state. So we always will be evolving those things because the life cycle of tech is very short. Okay? Finally, some references. Thank you, malware. Thank you again. And if you have questions, you can do it now, or later on you can find us near Siemens booth. Okay? Okay, no questions. Great, thank you. Oh, there is one. Yes.
Can you hear me?
Yeah.
Okay. Have you tried to build something to produce like phishing emails with machine learning or something like that, and put both systems like competing with each other?
Very, very nice question. Actually, I'm not sure if you look into the hackathon challenge. That's precisely the Siemens challenge. Okay, so I'm waiting for your answer. So I won't give you mine. Joking.